Alright, so for the problem today, we're trying to figure out how many of these molecules are polar. The first thing you need to do is to draw the Lewis structures for each of these molecules, and then from that Lewis structure you can determine the geometry of each molecule, and then from that you can figure out the electronegativities, and then from that you can assign bond dipoles and negative partial charges. And this will end up helping you find out whether or not the molecule is polar or not, and then you can also do it based off of the geometry of the molecule. First one we're going to start out with is OF2 to draw the Lewis structure for. And how you want to do this is you want to put the least electronegative atom in the middle. In this case it's O. And then you draw 2 bonds to each fluorine molecule. And then you want to count how many valence electrons are in it. And there is 20 valence electrons in this, so you already have 2 from each of these bonds, so you have 4, so you only need to draw 16 points. So you fill out the octets on the outside first, because each atom needs to have an octet. And once you have that done, you only have 18 out of 20, so you'd still have to draw 4 more of these up here, because you'd only have 16 done. So you need 4 more electrons. So now that's what it looks like when your Lewis structure is completely done. That's how you would do one. And then from here you can see that it has 4 domains. So it's a tetrahedral domain geometry, but for the molecular geometry it's going to be bent. So what you'll have is an O and the 2 F's. And then up here you'd have 2 non-bonding domains. And then based off of this, you'd also be able to figure out from just this alone which way the bond dipoles are going. So you go here, down, here, down, and it's bent for the molecular geometry. And then up here, back up to this, you can see this is going to have a partial positive charge because it's the least electronegative atom, and then on the outsides, on the fluorines, you're going to have that. Then you draw the bond dipoles here, goes out, and another one here going back out. They're equal. And then for the net dipole movement, what you need to do is you look down here and you see that both of them are coming down, so the net molecular dipole movement will be down. And because it has a net since it has a net dipole movement, this would make the molecule polar. Next, let's move on to SO3. First thing we're going to do is draw the Lewis structure for SO3. Alright. And then from here you need to make sure everything has an octet. So alright. And now what you need to do is assign the partial negative and partial positive charges. Here's where you put the partial positive. These are all the oxygens are all partial negatives. And then from here, all your bond dipoles will point outwards towards the oxygen atoms. And now you move on and you want to be able to draw the geometry. For this one, it's a trigonal planar geometry. And then after that, you know that since everything's pointing to the oxygens, you draw your dipoles. And then now, since all the dipoles are moving out from the center atom, away from it, and all of them are the same on the outside, all your domains on the outside are the same, this would make your molecule nonpolar, since there's no net dipole, because everything's tugging away from the center molecule. So there's no net dipole. And this makes it nonpolar. Next, we're going to move on to the BeCl2 molecule. And for this, draw it. Make sure you fill out the octets on the outside. And this little structure is special because for the BE molecule, it does not have to fill out octet. It's one of those octet violation rules. And so now you would assign the partial positive and 2 partial negative charges on the outside, and then put your bond dipoles going across. Positive head at BE and a negative tail at CL. And your geometry for this would be a linear molecule. And because the domains are the same, and since the dipoles are pushing away from each other, it would be a no net dipole again. No net dipole, and then it would be a nonpolar molecule. You can also look at, since the domains are on the outside of the same, it would make it a nonpolar molecule. Next, we're moving on to CCl4. For this one, all of these on the outside are going to have octets. Now we'll fill out your requirement. For your Lewis structure. Now what we're going to do is, since these are more electronegative, and these are going to have partial, since these are the more electronegative ones, you're going to have partial negatives on the outsides on all the chlorines, and a partial positive on that. And then because of all the outside ones being negative, all your dipoles are going to point out to the chlorines. And then you have a tetrahedral geometry for this. So what you would do is draw your C, Cl, and now since all the domains on the outside are the same, and the net dipole movement will cancel once again because it's all tugging away from the central atom, it would be a nonpolar molecule. Finally, we have O3. This one is different because all of the molecules are the same. All the atoms in that molecule are the same. Now, for this one, you don't have any net dipole or dipoles at all, or partial charges, because they're all the same electronegativity. They're identical molecules. But for this one, you could have a bent molecular geometry, and there would be 3 domains. And one of the rules when you use the geometry to find whether or not the molecule is polar is when there's 3 domains. When there's 3 domains, my bad, not that one. When there's 3 domains, if one of them is different, that makes the molecule polar. So that means this molecule would be polar. And common mistakes for this problem are people often will not put octets on the Lewis structures, and you could also use the wrong domain geometry or molecular geometry, and also you could assign the partial charges to the wrong atoms, and also you could get the net dipole movement wrong. And that is how you solve this problem.